Now,
But
what are
there
the
is a
values
catch
of
in
mu 0 and
producing that
epsilon
much
0?
of electrical energy, that
Permittivity,
much of
which is
heat,
denoted
and
as
to convert
epsilon
the
0.
heat into the
Epsilon 0 is the
electrical energy,
permittivity of free space.
we need a large
What
amount
does
of
that
power
mean?
in order to operate that power generator.
That means
And if
the ability
the
of
energy
any
input is
substance
greater than
which
energy
is placed
output, the
inside an
power
electric
generator
field,
won't be
the
economical
ability
for
of that
us.
substance
So we
to
don't need
store
that. We
electrical
need for a power
energy,
generator,
and for vacuum,
output energy
this
must be greater than the
permittivity
input energy.
is
But
of the order
the
of 10 to the
temperature
power minus 12 farad per meter.
the temperature is so high that we need a huge electrical energy to be used as input in order to get that amount of temperature for a successful fusion, which will produce sufficient amount of heat energy, which again produce electrical energy. Let's come again to the binding energy per nucleon versus atomic number plot. A bigger nucleus of atomic number A will be fragmented to produce smaller nuclei, and in this process the bigger nucleus gains some binding energy. Similarly, when two smaller nuclei fuse into a bigger one, it gains some binding energy. It raises up in the binding energy curve. Both the process involve some amount of energy release, say delta Q for fission reaction and delta Q prime for fusion reaction. But from this amount of energy, we should not get perplexed about the energy released in fission and fusion, because here 200 nucleons will be involved, but here 1 or 2 nucleons will be involved, and this is binding energy per nucleon. For fusion reaction, what happens is we have two smaller nuclei which will produce a bigger one. Some neutrons or gamma or other particles are produced, and of course some heat is produced. This heat will heat the steam, will make the steam expand, and that steam will make the turbine rotate, which will in turn produce electrical energy. So what mode of reaction is to be preferable inside the power generator, nuclear power generator? If we fuse two protons, we get two helium 2, but helium 2 does not occur in nature. So in reactors we will fuse deuteriums. Now deuteriums are abundant in nature because it is inside water. We got plenty of water, plentiful of water inside our sea. So here the fuel is cheaper, and this reaction produces helium. Helium is an inert gas, so there is no chance of radioactivity. And in this reaction, we have some heat output. This is the waste product, which is inert and non-radioactive. We get huge amount of energy. Fuel source is also cheaper. But what happens if we want to fuse two deuteriums? Deuteriums contains protons and neutrons. One proton, one neutron. When two deuteriums come closer to each other, these two protons come closer to each other. Neutrons will not have any problem. But protons are of being same electrically charged. There will be a Coulomb repulsion between them, which is equal to Z1 Z2 E square by 4 pi epsilon 0 R square. This is the force of Coulomb repulsion. And the nuclear potential would be like this. This already we have studied in our nuclear potential video, that when R is sufficiently small, the nuclear potential is attractive. But beyond that, there is a Coulomb repulsion. So when two protons are coming to each other, their distance is far big, and in this portion they are now here in this portion and they are facing Coulomb repulsion for each other. So how to make them fuse, how they come closer, so that we can bring them in this region and we could fuse them. At least we have to make them come at this point. So we have to give a minimum amount of energy which will be equal to the potential energy at this point, that is at small r equal to capital R. The value of the Coulomb potential energy at small r equal to capital R must be given to the protons of the deuterons in order to overcome the Coulomb repulsion between them, so that we could fuse them. So we will throw deuterons at an potential energy of this much. This is the minimum potential energy we should give to the deuterons. As Z1, Z2 equal to 1, so V0 will be E square by 4 pi epsilon 0 capital R, because small r equal to capital R here, nuclear radius, and this is a constant term, E square by 4 pi epsilon 0, this is constant, and E square by 4 pi epsilon 0 is 1.44 MeV Fermi. This will turn out to be, V0 will turn out to be 1.44 MeV Fermi divided by capital R equal to 2 femtometer, which is standard for hydrogen, and then we get this potential energy amount 0.72 million electron volt or 720 kilo electron volt. So the deuterons must be given a minimum of 720 kilo electron volt energy in order to get a successful fusion.